Hello everyone, I hope you enjoyed your lunch. So this is the second lecture now by Peter Kuchment about periodic operators. Okay.
Thank you. While the screen is still here, I want to say that although many things that we will be considering can be done on abelian coverings, unfortunately the condition of being commutative for the back group is hard to reduce. There are some cases when the most hopeful thing is if your covering is nilpotent, if the group of the covering is nilpotent, some things can be done there, but still it's really hard. You're stuck with the representation theory of this back group, which is not a nice thing to deal with. Okay, so now the Flaquet transform. Actually, Flaquet transform, it's not always called like this, sometimes without any name. Sometimes it's attributed to Gelfand, also physicists like Bloch knew this before him. But in any case, it's nothing new in comparison with Fourier series. So if you look at Fourier series, we discussed that Fourier series can be used representing functions on a torus, mapping functions on the torus into its their Fourier coefficients. But you can go backwards. You can, if you have a function on gamma, then you can use. So this is discrete function. It's labeled by gamma is like Zn. So you have a number labeled by integer indices. So you can add it up into and to get a periodic function. So here it is. So if you have, again, in order not to bother with this gamma, if you feel uncomfortable, think that it's just Zn, and whenever I have dual lattice, it's 2 pi to the power Zn. So if you have a function on this group, and sufficiently nice function, it should decay somehow so the series converge, then that's what the standard Fourier series does. You start with Fourier coefficients, you add them up, and you can write it in two different ways. You can write it, that's the standard way to write Fourier series, but if you replace the vector e to the power ik by the vector z, like we did in one-dimensional case, so z is e to the power ik1, e to the power ikn. Then it looks kind of more algebraic. So depending on what you're doing, you might prefer this or that form. So this is standard Fourier series. So if you have a function number, or actually you can look at vector valued version, if f gamma are vectors from some vector space, you can still do the same. The only thing is that your function on the torus will now take values which are not scalars but vectors from that space. And that's all you need to get well, for the Fourier series we all know standard L2 theorems, that L2 norms, depending on how you normalize, L2 norms of f gamma and f hat are the same. And we have, I would say, Pelley-Wiener type theorems, namely that say that if you know how fast f gamma decay tells you how smooth the function is. Now let us have a function. We don't have functions on gamma, we have function on the whole Rn. So let's do the following. We take a fundamental domain on W, whatever domain you picked, and you can say that this unit cube in our Zn case. And cover Rn with its shifts. Maybe I should draw this. So we have this fundamental domain W, and we covered the whole Rn by shifts. Notice that each shift is labeled by a lattice vector, namely by the vector by which you shifted. So this copy is labeled by this gamma. This copy is labeled by 0 vector, etc. And now you do the following, and you define. There is a formula, but it's better to understand this without formulas. What I do, I split my function on the whole space into family of functions on the unit cube. Those pieces of f. I cut f into pieces, and each piece is labeled by a vector gamma of the lattice. So for instance here it's another gamma prime. So what I have, and then I can think that each of those cubes actually shifted back. So what I have from one function on Rn, I get series of functions on the cube labeled by vectors gamma. So you see I split it into pieces, then I shift each piece back here, and what I get, instead of one function on Rn, I have a family of functions on W. And the next step, take Fourier series. Take Fourier series. So here, what's written here, it's exactly what I said, that I take piece of my function on this copy of fundamental domain, shift it back to the origin, and call it f gamma of x. So now Flaquet transform is just Fourier series which takes those f gammas as vector Fourier coefficients. What you get as a result, you get a function periodic with respect to case in this Fourier series, but its values are not scalars. The values are in the space of functions of x. So these values are vectors with the values in functions of, that's it, each vector is a function on W. So this is just a vector valued Fourier series. By the way, why should do this? The highbrow version says that since your problem is invariant with respect to group, you have to do Fourier analysis in this group. You have to do Fourier transform in this group. A group is abelian, so you have to expand into characters, and that's what we do. Those are exactly the characters of our group gamma in this expansion. But if you don't, some of you haven't learned some of those words, you can completely disregard everything is here.
Physicists sometimes call this the Zach transform.
But I thought that Zach is mostly when you have magnetic translations.
That's one way of using it, but it's still, it's
Okay.
it's this structure.
Okay, I thought that Zach applied just to magnetic translations only, but I don't know.
No.
I mentioned that this name Flaquet is kind of strange. It's better to avoid any name here, not to get in the middle.
You need a plus sign there in the definition of f gamma. X plus gamma.
Probably.
That's plus.
Yes, that's plus. When I was writing this, I felt that I have too many pluses and minuses, and I'm always lost when I have.
This is now you offer this to audience to choose.
But I would have said the plus is on the subscript.
Yeah, You're right. Either way would do. But this is wrong way. This is the right way. The picture is correct. And you put pluses, minuses the way it should be. They should be. Typologist P.S. Alexandrov once said that he invented some, I think it was homology, Z2 homology, since he couldn't keep his signs straight. In Z2 it didn't matter. Okay?
In your exponential, you have letter L there?
It should be I. It's an I.
That's an I. That's a lowercase I that became an uppercase because it wanted to grow up. But that's an I.
Yeah, it's
Square root
an
of
I.
-1.
Okay.
Well, it's interesting.
It is
It's
uppercase I.
everywhere.
It's the square root of -1.
Yeah.
Which one? Okay.
We work mod Z2.
Okay, so this is essentially what Floquet transform is. It's nothing but using pieces. You chop your function into pieces. And this is useful picture since somewhere later there will be an issue that is easy to understand here, but harder to understand in formulas. So now, as I said, these are just, oh, it's plus here.
Cover.
Yeah.
Point to be right.
This transform has some interesting properties. The resulting function has some interesting properties. With respect to shifts, you see you have x and k, and you can shift x by gamma vectors and k by gamma star vectors. If you shift k by gamma star vectors, you expect what happens. The function actually is periodic with respect to k. It's Fourier series, so it will not change. But if you shift by gamma, by x by vector gamma, that's what happens. So you earn this factor. So sometimes you say that the function is automorphic with respect to x with this character. And here is normal I. I don't know. And as I said, it's periodic with respect to x gamma star periodic just by design. It's Fourier series. So you get periodic function. Okay, so this is the transforms that helps a lot studying periodic problems. Now, inversion formulas. Since it's Fourier series, we know how to invert it. But there are strange things here. There are two inversion formulas. And why is that? The second formula is more understandable. What it does, it actually computes, what is it? I might have another.
X minus gamma perhaps.
No. Oh, but k cannot be minus gamma. There is definitely an error here. So let me figure out. Let's look at this. At the first formula. It looks strange since when you invert Fourier transform, when you invert what we assembled Fourier series into periodic function, how do we disassemble it? We multiply by exponents and integrate, and there is no exponent here. So this is a very strange formula. It looks like we are recovering only the zeros coefficient of this function. So, here is an explanation. If we write down our Fourier series, what notation gamma here? then the first term is just f of x. That's a zeros coefficient. And then there is everything else. And so when we write this, it seems that we only recover the zeros, this zeros coefficient, we only recover this part of the function. But actually we recover everything, and the reason is this property of the function u. This property of the function u. Since I said that in this transform we restrict x to the fundamental domain, but we can allow any x in this formula anyway. Then we have this relation, and so what happens is that this relation tells you that actually you recover, if you allow x to go around the whole space. If, for instance, instead of x in w, you take x in shifted w, there is exponent automatically arising, and you recover the Fourier coefficients. So this is correct. And this should be exactly that thing, but somehow it is written wrong. Oh, there shouldn't be minus gamma here, I think.
X minus gamma?
So it should be probably x minus gamma. But I cannot think at the blackboard. Actually, what is written here, that's what I just said, that if you shift x by gamma, you have this popular. So apparently it's x plus gamma here.
Or
x minus. Oh, it's x minus.
You want f of x everywhere. X runs around Rn.
Again, plus and minus. And I cannot handle those.
You define Fourier transform for all x in the entire space, or is it in the fundamental domain? I'm just trying to.
Yes, that's what I said.
If you could.
I just said you can use this formula not only for x and w, but for x in the whole space. And then you have this relation.
If you interpret f gamma not with the restriction there,
yes,
but in fact,
yes,
as the
just
f
shift
of x might just
shift of f. That's what I'm saying. That you can consider f gamma of x. Thank you, not as a piece of this function shifted here, but the whole function shifted. Then you have this property, and then this property will give you the missing exponent in Fourier inversion formula. So you need to correct it appropriately. That's a home assignment. I cannot do anything correctly right here. So, just a second. Mm.
So it's the x that should be translated.
Yeah, but still, I cannot.
In which case?
It might. Yeah, it is just. You don't need to shift x at all.
It looks
Oh
strange.
yeah, x, yes, x plus gamma, right?
First way you've replaced
Yeah.
f of xk by that earlier formula you have on the slide
It will
before.
be the same. Yes.
So
Yeah.
if you just put that in for u of xk,
Yes. Yeah, you're right.
except for the signs.
Yeah, but since we already agreed that
Which we've already
don't
agreed.
matter.
You use
So this
quantified
is,
little ones.
yeah, this is definitely a mistake. You cannot subtract gamma from k since they live in different spaces. But if you put, the previous formula tells you that you can put this exponent to compensate shifting here. So that's Fourier transform, which is just, as Barry said, it's called Zach transform in physics.
We also do mathematics.
Yeah.
This paper of Hernandez et al. On Zach transforms that
But
derive.
I've seen also the name Gelfand, which I don't think should be here.
Actually, there's reason for that. So
Yeah, I know this for Gelfand, but it's better not to get in between in those cases.
it's also claimed that it's sometimes called the Weil-Gelfand transform.
Oh,
They had a formula related to this too.
I didn't know anything of that. Okay, since we have Plancherel and Pelley-Wiener time theorems for Fourier series, what Floquet transform is just Fourier series with vector-valued coefficients. And all those theorems, if you have vector-valued coefficients in a Hilbert space, then all those formulas stay for Fourier series. And therefore, we automatically get that, for instance, that this transform is an isometry from L2 on the whole space into L2 on the dual torus with values in this Hilbert space. We have, if you, we will need in elliptic theory, normally we will need smoother spaces. So if you have a Sobolev space of some positive smoothness, then you can do the same. The only thing is that what happens is that somehow it's isometry of this space. You would expect that since each of those pieces is, if your whole function is in HS, each of the pieces is in HS, you would expect maybe isometry of HS in the whole space onto this L2, but it's not the case. There is simple reason. I will address it in a minute. So actually, this is isometry of HS onto a proper subspace of this L2 space. And it is important.
Do you get the sort of Dirichlet subspace? I mean, you take the function with compact support. And No?
I will explain this. And we also get for free the Pelley-Wiener type theorems. For instance, that the exponential decay of L2 or HS norms of F on those pieces means analyticity of this transform in some neighborhood of the torus. These are standard Fourier series theorems. And there are other theorems that if you have some polynomial decay rather than exponential, some power decay, you get some smoothness. All those things come from free from Fourier series. But there is something, the only strange thing is this. So what is wrong with HS? And here is the explanation that you have, the direct transform works as follows. You chop your function into pieces, then you shift them back to the same fundamental domain and use them as Fourier coefficients. Now, inversion would do the following, that you take this function depending on k periodically with values on this fundamental domain, and then you expand it into Fourier series, you get those coefficients, and you shift them back, you put the pieces in their places. But now the question is whether they will match. If you were talking about, so what I'm doing with HS, you see what is not true, that it's not onto. And I discuss why it's not onto. If you start with this space and try to unfold it to get back the function here, what you will get a function which is in HS in each of those boxes, but there is nothing that guarantees that they match across the boundary. When you are in L2, there is no matching. That's why everything was fine. So, but when you try to invert this guy, you'd get not function from HS, you get function from HS on each of the cubes whose sum of square of the norms in HS finite. But it doesn't mean that it's in HS, since we didn't enforce smoothness across the boundary. So this can be, so that's the explanation that I gave you. So what we need to do something to make sure that they do match. And now I do what I already have mentioned. You consider the same transform, but without restriction onto the fundamental domain. Before, this was f gamma, which was restriction of this function on W. I don't restrict it anymore. I take it in the whole space. Then we get this property, as I already have mentioned, this A sub k property. It should be satisfied for every k. I already have said this, that it's called automorphic or cyclic or quasi-periodic with respect to x with this character. Let us now introduce the following space in the whole. I introduce space HS sub k. For each k from the torus and fix S, I introduce a closed subspace of our. We saw that we don't get the whole space of function like here. What happens? I need for each k from the torus, I need to choose a subspace in this HS space, and here is how you introduce it. So consider all functions in HS locally in Rn. Locally, since the condition I'm going to impose will prohibit that they are global HS, such that they are automorphic like this. For a given k, they satisfy this for all gamma. This condition prohibits the function to be HS in the whole space, since this is modulus 1 coefficient, so those norms will not decay. But then take restrictions of such automorphic HS log functions onto the unit domain, fundamental domain. So, in other words, these are all HS functions in the cube W, which can be extended automorphically, remaining in HS locally. And it's easy to check that it's closed subspace in HS. By the way, if S equals 0, this is the whole space L2. Since any L2 function can be extended like that. So you don't need to enforce boundary smoothness. So for L2, this is no restriction whatsoever. Every L2 function on this cube W can be extended on other copies of the cube according to this formula. So it's not a subspace in L2 case, it's just a whole L2. Now, the range theorem for HS space holds true if you do the following. So let me draw a picture. So you have your torus, T star, and over each point of this torus you have space HS hanging, HS of W. The same space is just direct product of torus with this space. And now for each k, if I have k here, we have this subspace HS sub k. And this subspace rotates when you move k. It rotates with the layer, so it changes with k. It's easy to prove that it moves smoothly. Actually, it moves analytically. In what sense? For instance, it's easy to construct a projector here that's called P sub k, from this HS onto this subspace, which analytically depends on k. So it's very nicely changed in subspace. And some of you might know how we call such things. If we now only keep those subspaces and erase the whole space, this rotating thing is called vector bundle over T star. So before we had this direct product, for each k we had a function here. Now this space starts rotating depending on k. Instead of the same space over each k, you have this rotating subspace. So this is what is called a vector bundle, and actually it's analytic vector bundle. This means that those spaces rotate analytically. It's easy to prove. And now this is the vector bundle I'm talking, this calligraphic HS. By definition is the union of all those subspaces over T star with a natural projection onto T star. And as I said, it's a vector, analytic vector bundle. And now the correct theorem is that the image of the space HS, oh, I didn't write it. Now the space HS in Rn is isometrically mapped onto the space of L2 sections of this vector bundle. What does it mean, L2 sections? It means that first of all, the L2 functions of k, and then for each k it's not arbitrary function HS, it should sit in this subspace. That's what it's called section. So that's why we didn't get the whole space L2 T star HS of W, since the condition is that for each k you should be in this specific subspace of HS. And this condition changes with k. And that's crucial. There is a lot of geometry here with this, but I wanted to give you a feeling of this. There is another interpretation. That instead of saying that we how to explain it? Well, if you have a function UF of xk, it's not periodic with respect to x. It's not a smooth function on the torus, since when you shift x by gamma, this factor pops up. If k is 0, it's just periodic function. But if k is not 0, it's not a periodic function, which is not a very nice thing to have. We start having some kind of, you can consider this a boundary condition on W, which is not the best thing to do. How you can interpret this differently, I will not use it later, but so if you skip this part, it's okay. But what can be done, instead of scalar valued functions, you can consider functions as sections of a linear bundle over torus. Scalar functions are sections of trivial bundle, torus times complex numbers. So it is like, if this is torus, it's like the strip. But we see the problem that it's not actually function on a torus, since those parts don't match. It's not periodic. What you can do, you can force this one-dimensional space rotate by itself, and glue together to this part with this condition, with this factor. Something like Möbius strip. If you do this, you get a nice smooth linear bundle over the torus. Linear means that each layer is just C. And then our functions are just sections of this linear bundle. And this condition is enforced automatically, since when your section reaches here, it exactly pops up there with this factor. Why is it, again, I will not dwell on this, so you can skip this part. Why is it useful? Since maybe it's just esoteric stuff which is not needed. The useful thing is that we eventually will end up on with our operator acting on the torus, on a compact manifold. But acting on the torus means that it's acting on periodic functions. And our functions are not periodic. They are, you see, automorphic. And there are two ways to deal with this. One is to consider functions on the fundamental domain and just enforce the boundary conditions. That the value here is the value there times e to the power, just boundary condition. Another, and this is possible, but it's not very nice to work with boundary value problems, especially in non-smooth domain. But if you talk about linear bundles, everything is smooth. You end up with elliptic operator in sections of linear bundle under the torus, and the whole, people who don't know this, you should believe me that the whole elliptic theory works nicely for those. And you don't have any need to impose any bound. Instead of working a boundary value problem for elliptic operators, you will work with elliptic operators on the torus with no boundary whatsoever, but it acts on sections of linear bundle. Now, after all this effort, I can tell you that you can forget it, since it will not influence anything later. But it is important way to looking at things. So I said that, just said that the advantage is that instead of dealing with boundary value problems, with boundary conditions that depend on quasi-momentum and the domain is not smooth, you have nice elliptic operator without any boundary on the torus. And again, it's avoidable. So what is the bottom line? So we return to our periodic operator H in Rn, and now apply the Floquet transform or exact transform or whatever it is. Since the operator is periodic, it preserves our automorphicity condition. Automorphicity tells us that the function shifted by a period gets multiplied by something. And since the operator commutes with shifts by periods, it preserves this condition. And therefore, it preserves this subspace. And what we do get now, for each k, we get operator h of k in L2 whose domain is not the whole H2. 2 since it's second order operator, but H2 sub k. In other words, if you don't like, if you prefer boundary value problems, you get what is h of k. It's the same operator in the fundamental cube, which with boundary conditions that when you shift your function from here to there by vector gamma, it just gets multiplied by it. And the same for the normal derivative, second order operator. The same here, you just shift by different gamma. So h of k is your restriction, your operator in the unit cube with those cyclic boundary conditions. For each k, for k is fixed here, for a given fixed k, whenever you shift by a period, you get this factor for function and its normal derivative, and the same in each direction of periodicity. And alternative point of view is with bundles. And so what you get a nice elliptic operator. Nice elliptic operator. And the whole elliptic theory applies to it, and we will see what it does later. So what we get this transform essentially does the following. It identifies L2 functions on Rn with L2 functions on torus with values in L2 on W. And that's exactly what direct integral means. I will not get into details with direct integrals. And the direct integral expansion of HS is similar, except that this, for each k, in L2 case you had the same space. Now for each k you need to take this subspace. And the operator correspondingly expands into direct integral of those operators h of k. So h of k acts on this subspace hsk. Or, if you will, h of k is your operator in the cube that satisfies those cyclic conditions. Now, before going further, what is the advantage of doing this? Instead of studying one nice operator, we get the whole family of operators that depend on some quasi-momenta, etc. So what is the advantage? The advantage is that the original operator was operator in the whole space. And as you saw already in David's talk, and you will see again, and you saw in 1D case, the spectrum is continuous. However, for each k, h of k is elliptic operator on a torus. And elliptic operators on a compact manifold, they have normally, except some pathologies, they have discrete spectrum. So we expanded operator with continuous spectrum into direct integrals of operators with discrete spectrum. And what is h of k explicitly? One way to understand it is already this. I already told you that you consider your operator in the unit cube, and you enforce the domain is h2 functions such that the functions and their normal derivative satisfy this cyclic property, that when you shift from here to here, you get the corresponding factor. That's one way to see it. And what happens here, you see that the expression for the operator looks the same. Doesn't depend on k. But what depends on, but they are not the same operators. Why? Since their domain rotates. You have fixed operator over rotating domain. But you can do alternatively. You can fix the domain and the operator starts rotating. And how you do this? You see, if you have a function with this cyclic condition, you can divide it by you can represent it as a function in the form e to the power ikx times periodic function. Then this exponent e to the power ikx can be commuted with your operator, and only periodic function is left. So the result will be that your operator will act on a fixed domain on the periodic functions, on the torus. But the price you pay is this, that when you commute, when you do things like that, when you take minus delta and apply to e to the power ikx v over p of x, where p is periodic, and then you remove this, simple calculation shows that if you write it as an operator acting just on p, this is the operator. Again, I don't guarantee any science, but should be correct. So this is what happens with delta. V doesn't change since multiplication by a function commutes with multiplication by exponent, so it doesn't change. So you see, instead of varying domain and fixed differential expression, you have varying differential expression with fixed domain. Now, which one is better? Both are, or none is. The thing is that depending on what you are doing, one of these two representations can be more beneficial. This thing is nice. It's a very simple algebraic expression, algebraic dependence on k. However, what you lose here, you don't see from here directly that there is no explicit periodicity with respect to k here. Your things should be 2 pi periodic with respect to k, and they are. But it is not clear here. It looks like this is not periodic, but you can check that if you shift k by 2 pi, the resulting expression is unitary equivalent to the previous. So it's a price you pay, and again, every time you have to make judicious choice, depending on the problem, which way you work, either this or that. Okay, and now finally I will get, this is the end of preliminaries. That's something that many of you already know, and you who hadn't known, you see the sketch. Now I will get to the serious stuff. The next part will be dispersion relation and things around that. So first of all, I will just define dispersion relation, also called Bloch variety. I will discuss its analyticity. I will discuss its irreducibility. Then I will discuss where the extrema can be located, how can they look like. I will discuss when dispersion relation has so-called Dirac cones, shaped like this. This is something important nowadays due to appearance of graphene and other materials. I will discuss Bloch bundles, which are important, for instance, due to topological insulators, or from numerical point of view, from trying to use a very nice basis of so-called Wannier functions, which I will introduce. I will discuss Fermi surfaces, and a little bit I indicate what is known about inverse problems related to all this. I want to warn you that if you haven't seen this stuff before, it will look kind of esoteric somewhat. For instance, things like irreducibility, this is something from algebraic geometry, from geometry of complex analytic spaces, etc. And why is it important? But later on, when I switch back to spectral theory, you will see that all those things are important for different issues in spectral theory. And that's why spectral theory of multidimensional periodic operators is complicated, since you have to deal with complicated complex analytic geometry, sometimes algebraic geometry, etc., and it is hard. That's why, as you will see, results are not nearly as good as we would want. So that's what I will do. In the remaining time, I will introduce dispersion relation and maybe discuss something about it. So what is a dispersion relation? We have already seen one briefly in 1D. It is the relation between spectral parameter lambda and quasi-momentum k. Remember the picture where I discussed monotonicity of branches? That was dispersion relation. So let's define it. First of all, for each k, our operator h of k, again, it's our original operator with depending on k boundary cyclic conditions. It is, since it's operator on a compact manifold, it has discrete spectrum. It's not always the case, but we have enough good structure in operators that it's true. And since I chose the sign minus delta, this operator is bounded from below. So this means that it has discrete set of eigenvalues going tending to infinity. And there could be multiplicities, so I list, if there is multiplicity, I list this, if it's triple eigenvalue, call it lambda 1, lambda 2, and lambda 3. So equalities are allowed. This is the spectrum of this operator. Now, you can consider this set as a function of k, multiple valued function of k. For each k, I have this set of values. Each of those lambdas is called, lambda 1 is called the first band function, lambda 2 the second band function, etc. Those band functions, they are known to be continuous. This is a simple thing from perturbation theory. And they are piecewise analytic also, which is less trivial thing, but also not very hard. We'll return to this. So those functions, lambda of k, they are piecewise analytic. And so we consider this multiple valued function. For each k, we take the spectrum. And the graph of this, either this function itself or its graph, is called dispersion relation. So let me draw it a little bit. You have this multi-dimensional k, so it's not one-dimensional now, and this is lambda. So when we fix the value, some value of k, then you get a discrete spectrum of lambdas. And then you start varying k, those lambdas start changing and moving. They move continuously according to perturbation theory, but they can collide, for instance, and they can do weird things. But whatever happens, you get this big graph. It's kind of surface in n-dimensional, if k is n-dimensional, this n-dimensional surface in n plus 1-dimensional space. And this is what is called dispersion relation. So dispersion relation is a relation between lambda and spectral parameter or energy and crystal momentum, quasi-momentum k. And its graph, the surface, is called also Bloch variety. So Bloch variety is this whole thing that I drew here. Here is exact definition. So Bloch variety of operator H is the set of all k lambda. Now look, I allow k and lambda to be complex now, and it is important. So far, from what we did, it looks like we only need real k and real lambda. But the properties of this surface can be hidden in a complex domain. Important properties can be hidden there. So I allow it to be complex. So what is this? K lambda belongs to Bloch variety if and only if lambda is eigenvalue of h of k. In other words, h of k u equals lambda u has a non-zero solution. And nothing prohibits you to allow k and lambda to be complex. For instance, if you remember this algebraic expression with k and k squared for your operator, nothing prohibits you from considering complex k. So this is a Bloch variety. And as I already said, you will see that it's important to understand the complex Bloch variety, although it looks like we only see its real part. And here's an example of a block variety. Certainly drawn, it's in dimension 2, k is 2-dimensional, and certainly everything is real. Vertical lambda is real and k is real. Otherwise, it would take 6 dimensions to draw it. So that's, you see, that's lambda 1, this is lambda 2, lambda 3. They are not always, I probably haven't picked nicest. It's too nice of an example. It doesn't do some weird things that block varieties can do, but still, that's an idea. So that's a graph of lambda 1, this is lambda 2, lambda 3. They can collide, they can form cones here, and they can do many weird things. Okay, so that's block variety. Now, what is it for a free operator? They actually did this in 1D already. You remember parabola and its shifts. And it's exactly the same in n dimensions. You imagine that this line is multidimensional, so you have paraboloid now shifted by periods. And then you restrict it to Brillouin zone, to one of those, only to one strip here. And you see this picture of many branches. So even for a free operator, if you do this and draw it, it will look complicated. Also, it is not. Okay. Now, a little bit about the spectrum. I told you that I will return to the spectrum later, but a little bit about the spectrum. So the spectrum of the whole operator, one can prove that it is the union of spectra of all h of k's. I will not do this proof here. It's a little bit more technical than I want, but if you look, h is represented as multiplication by operator valued function. Now imagine operator multiplication by scalar function, continuous scalar function. Then the spectrum of this operator is just the range of this function. Now imagine that you have operator of multiplication by a matrix valued function. Matrix is self-adjoint. It's not hard to prove that you need to take the spectrum of each of the matrices and take the union. And this is just infinite dimensional version of this. So the spectrum, one can prove that the spectrum of operator H is the union of all those spectra. So you can write it as follows. What are those spectra? They are points lambda j k when j changes and k changes. Now if we take only union over k for the fixed j, since lambda j is continuous function, this union is in a closed interval. You have a continuous function on the torus, its range is closed interval. So if you take union over k only, you replace this spectrum is union over j, and then you take union over k. You switch the order. You take union over k first, and then this gives you the j's band of the spectrum, which is a segment, just like this. So this is lambda 1. This is lambda 2. This is k. So if you take the range of this lambda 1, it is the first band of the spectrum, I1. If you take the range of lambda 2, it will be the second band of the spectrum, I2. In this case, they are touching. However, if you have a picture, something like this, that the band corresponding to lambda 2 will overlap with the band corresponding to lambda 1. But this is what this union is. So in other words, what we conclude that the spectrum has band gap structure. Again, like in 1D, it's a union on finite intervals. Why finite? You have range of continuous function on a torus, on a compact. It's It's compact interval. That's a union of bands, finite intervals, that shift to infinity. However, now they are allowed to intersect, overlap. This range is called the J spectral band, and bands can overlap. So these things that we prohibited due to monotonicity in 1D can and do happen often in multidimensional case. And the last thing I will say here, it is rarely mentioned, but it's frequently used in different circumstances. You actually don't need all values of k. So what is written here, you take the union of spectra of h of k over the whole torus of k. You don't need all values. If it's enough to pick a dense subset of values k in the torus, take the union, and then take the closure. And it's trivial, but it's very useful. For instance, you might have some value of k which you hate, and not due to your personality. For instance, if you consider Maxwell operator, you go extra lengths to avoid k equals 0, which is not a nice point. You want to avoid it, okay. You can avoid it. And there are other applications, as born for von Karman method I will explain later. It's also part of this. So you can restrict yourself to a dense subset of quasi-momenta, take union, but then don't forget the closure. Okay, that's all.
Thank you very much. Questions? Everything seems to be clear. Just go ahead.
Well, I understand why allowing k to be complex is important to get the algebraic structure out of it, but aren't all those hk self-adjoint anyway, so lambda will still be real even if we...
No, they're not.
Okay, they're...
For k, it's clear from the formula. If you look at the formula of h of k that I wrote, when you make the domain fixed periodic functions, k enters the formula. If you look at this formula, you will see that it's not self-adjoint anymore.
Oh yeah.
Even in the case v equals 0, it's
Yes. Yeah.
All right, thank you again.